Okay, everybody's with me here. Can you guys hear me? We need maybe like 30 seconds. People online, can you guys hear me? Yes, okay. Samuel, Miriam, and Marine can hear me. That's very good. That's a good sign. 3 of you can hear me. Okay, great. So let's get started. So I mean, of course, this is not an exhaustive list of what is everything, but this should give you an idea of what to expect. Okay, so the first thing, could you give us some advice on what to focus on? Yeah, I mean, this is what it's about. This is what it is about, right? Okay. Great. So this is the material will be for groups. Of course, if you want to know all the groups, I think the midterm review gives you a good overview of the pre-midterm material, right? There is I think I did a midterm review, and I think it's still online, so you can do it for the pre-midterm material. Now I'll go on the post-midterm, a small recap on the not post-midterm, but post-whole grade midterm. Group theory material. One more question. And could you elaborate on the homework announcement? I don't know what is the homework announcement of yesterday. Could you? Yeah. Anyways. Okay. So the group theory material. What is the first thing that we saw before at the beginning after the break? Group homomorphisms. Okay. So the definition of a group homomorphism. G and H are groups. What is a group homomorphism? I'll be a bit sloppy. I'll not write every single thing because, right? It's here, right? What is a group homomorphism? It's a function row. So let's write from G to H, such that what? Row G1, G2 is equal to row of G1 of G2, where every operation is happening in the group, in the corresponding group. Okay, this is multiplication in H, this is multiplication, right? Then we saw that row of EG is equal to EH, and row of G inverse is row of G inverse. Right, these two properties of homomorphisms that we have seen. You remember that? Then so the homework message yesterday, I've seen a lot of things that I've entered in the homework, and I've seen many things that we have not seen, that we will not see, or that we have not seen yet. So in the final exam, should you use something that we did not see in the lectures or in the homework? You should prove it. Okay? You cannot use a theorem that we did not see in the lecture. Okay, so this is a group homomorphism. These are the basic definitions, basic properties. Now, what's another thing? The kernel of a group homomorphism. What's the kernel of a group homomorphism? You have to know how to define the kernel. Right? Or this is row inverse. H. What are the properties of the kernel? Per row in the subgroup of G. Not only is it a subgroup, but it is a, let's say, normal subgroup. If you want me to prove these short proofs, I can do them now. If you want me to do that, I can do them. So, for example, one question could be on the final: true that the kernel of a group homomorphism is a normal subgroup. That's easily 10 points. Very easy. Doesn't have to be very long. Okay, that could be a question. Like things like that could be questions as well. Short questions, just to make sure that you know how to do them. And then what as well? Rho is injective if and only if what? The rho is equal to EG. We remember these three statements. Rho is a subgroup, rho is a normal subgroup, and rho is injective if and only if the kernel is the identity subgroup. Okay. Should I prove these, or that's okay? Should I redo the proofs, or we're fine with them? We're fine, right? Yeah. Are we fine? Or should I do that? I could do one of them, I could do two of them. Let me know.
Personally, I've forgotten them, but I don't mind like looking through the lectures and finding them.
Yeah, I mean they're all in the notes. They're all in the notes. So like if you want, if there's something you don't understand, I can do that. Yeah.
But which lectures precisely that?
I don't know. I don't know what the number is. So you have to look.
Yeah, okay.
I mean, if you look under lecture by lecture, I give a summary of every lecture. So you can go and find it there. Okay. Yeah. The last one, we prove the last one? Sure. So rho is injective if only if rho is the identity. So what is it? So suppose rho is injective. And let X be in rho. Okay. What is rho of X? Then rho of X is equal to the identity in H. Agree or not? Now, what is the identity in H? It's also the identity, this row of the identity in G. Agree or not? Yeah, which is equal to rho of EG. Can you say that X is equal to EG? If rho is injective, can you say that X is equal to rho? Since rho is injective. And rho, then X is equal to EG. So rho is equal to EG. Of course, I mean, it's clear that EG will belong to rho as well, because rho of EG is equal to EH. Okay, so you don't need to prove a double inclusion. You know, this is good thing, it's obvious. Okay, now the other part is more interesting. We've done these in the lecture, right? We've done this one, yeah. Okay, so rho is injective, and then what as well? So suppose rho is the identity. I mean, of course, rho is a homomorphism. Rho is a homomorphism. Of course, right? Rho G to H, otherwise the group. Suppose rho is equal to EG, and let xy be in G be such that rho of X is equal to rho of Y. What can you say? People attending online are also welcome to help.
We can bring the
Sure, that's very good. Let's bring the other side. So rho of X Y inverse equal to EH, right? This is an operation happening in H, right? Rho of X is in H, right? Yeah. Now what can we say? We can use the other part to say that this is rho of X, rho of Y inverse, the previous propositions. I mean, these you can use without proving. If the question is that if the question doesn't say to prove them, you can use them without proof. Right? Rho of X, rho of Y inverse is equal to VH. What can I then do? What do I know about rho? XY inverse. Very good. So this is rho of XY inverse is equal to VH. So this implies then xy inverse. This implies that xy inverse belongs to her row is equal to EG. So xy inverse is equal to EG, but that's equal to y, hence rows. Okay. Is it clear? Any questions on this one? Yeah.
Let's say in the final, you know how these questions you have to put it both ways.
Yeah.
So let's say this question we have to put it both ways, but you can only do one way. You know how sometimes one way is much longer than the other way.
Yeah, I don't know. That I don't know. You know, most of the time, yes. Most of the time, yes. But I don't want to. It's not binding. You know what I say here is not binding. Most of the time, yes. If you have something like that, I'll just do it 50-50. Okay. Any questions? Okay. People attending, do you have questions? Online? Okay. Okay, is it clear? So far, so good. So these are three things. These are mainly on the kernel. This is you have to know. Now, what's the next step? The first, I really want to do. I mean, isomorphism. So row from G to H is an isomorphism. What is an isomorphism? Is a bijective. Homomorphism, right? Yeah. Now, I mean, you should be able to tell me if two groups, when you should tell me if I give you or find whether or find usually find whether two groups are isomorphic or not. Right? For example, classic question, what would it be? Find 5, let's say, non-isomorphic groups of order 6 of order 8, sorry. Right? Or find the 3 find 2 non-isomorphic groups of order 6. Find 2 non-isomorphic groups of order 10. And so on, things like that. Right? And how do we do that? We find a feature in one group that is not present in the other, right? So you find an element, say, if you want a billion, not a billion, right? S3 and Z mod 6Z are not isomorphic. Why? Because S3 is not a billion, but Z6 is a billion. Both of them have 6 elements, but one is a billion and the other has, but the other is not a billion. Yeah. N? No, row G to 8 is an isomorphism, is an if row. If it's bijective homomorphism. It's a bijective homomorphism. That's an isomorphism, right? It's a bijective homomorphism. Yeah.
Well, can't you just, let's say you were given a homomorph group, can't you just prove it's injected and then surjected and be like, therefore?
Yeah, but you might not be able to find one. You may not be able to find a bijective and a surjective.
So this is the like alternative.
Well, I mean, if they're non-isomorphic, then there cannot exist an isomorphism. Because isomorphisms means that their group structure is the same. Exactly the same. One is just in disguise, the other in disguise. So it's just the other wearing a mask. Anything funny I said in disguise?
So it's just rearranged differently.
Exactly. That's the word. That's the word. If you want, it's rearranged differently. It's a different relabel. I didn't say that explicitly, but you're just labeling your terms differently. Okay.
Can we do like a short example if that's possible?
Yeah, sure. Sure. Write down to non-isomorphic groups of order 6. How many groups of order 6 you know?
3.
S3 is 1. What's another one? Always Z mod 6Z. Right? Z mod NZ is always a group of order n. So Z mod 6Z and S3 are they isomorphic? Why is that? This is a billion. And this is not a billion. Okay, let's do it with order 4. Could you do with order 4? Well, I mean, yep. Order 4. So you have Z mod 4. S2 has order 2. Yeah. Yeah, sure. Yeah, we'll do some examples like that. Of order 4. How many groups of order? I have Z mod 4Z and what as well? No, of order 4. Yeah, that's it. Z mod 4 and Z mod 4. Z mod 2 plus Z mod 2. Are not isomorphic. Does the abelian argument work? Can I say one is abelian and one is not here? Or both are abelian? Are both abelian or not? Yeah, both are. Both are abelian. Both are commutative, like the group addition is abelian, right? Plus, right? Yeah, we know what an abelian group is. We remember that? Abelian group is the operation is commutative. When it's have addition, it's commutative. Now, why are these not isomorphic? Yeah.
The order of the
The order of the elements, very good. So, what can you say? Yeah, sorry, that's the one. What do you mean? These are different. Exactly. So Z mod 4, what is the highest order you can find? Z mod 4. The highest order is 4, right? 1 has order 4. In Z mod 2 cross Z mod 2, what's the highest order you can find? 2. Exactly. So they're not isomorphic.
Since they don't have the same.
No, since you have an element of order 4, and there you don't have an element of order 4. Okay. Yeah. Are we good here? Yeah.
Why is S3 not commutative?
Write down 2 permutations.
1,
1, 2, and 1, 2, 3. They don't commute with each other.
1, 2, 1, 2, 3 is not equal to 1, 2, 3.
No.
Good point.
Okay. Now, so let's say Z mod 6 and Z2 cross Z3 are they isomorphic? Z2 cross Z3, is it isomorphic to Z6? Yeah, they are isomorphic. Why is that? By the Chinese remainder theorem, right? So for example, if I can ask you, show that R Z6 and Z2 cross Z3 isomorphic. What does the Chinese remainder theorem say? It says that Zm cross Zn is a cyclic group of order Mn if and only if M and N are relatively prime. Remember this? So what is this? These are isomorphic. Yeah, you have to know every single theorem. Every single theorem is questionable, but it's not infinite. I mean, we'll see in a stronger version. We'll see in a stronger version that these are isomorphic as rings. Yeah. Yeah, you can say by Chinese remainder theorem. 2, 3 are relatively prime. So Z mod 2 cross Z mod 3 is isomorphic to Z mod 6C. You can use the theorem immediately. 10 marks, free.
Unless it says proof of theorem.
No, unless, yeah, exactly. Unless I say, and find an element of order 6 in Z2 cross Z3. Then you have to be more specific. Okay. Sources, should we use lecture notes and tutorial or go to and practice on the algebra textbook as well? So when I wrote the final, I didn't look at the textbook really. Okay, so it's better to look at the notes and homework and tutorials. These are the best practices you can do. Okay. Yeah. You have a question?
Just answered.
Oh, okay. Thank you. Okay. Any more questions? Yeah.
This textbook is not like the
No. 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 I make my own notes, and I usually make my own problems. So like, there is no. Yeah. Usually I make my own notes. So I mean the group action part is not entirely covered in the textbook, if you noticed. Right. So it's yeah. Okay. Any more questions on this? The Chinese remainder theorem. Okay, so I mean we will continue with this. So then I mean, yeah, could anyone give, well, I mean, groups of order 10, let's, groups of order 8, can you give me 5 non-isomorphic groups of order 8? Start constructing. How do you start constructing a group of order 8? What's the first one you know? Z mod 8Z. Great. Now, what's another one you can do with products of groups, right? A good way to generate a billion groups or not a billion groups with products. Z8. How can you decompose the 8? Yeah, very good. So I have Z4 plus Z2. Then Z2 3 times. Very good. I have 2 more. D4 and D8. Very good. D4 is a hidden group on 4 elements on a square, right? The signatures of a square, and the quaternions. And these are all the groups that you can find. Any group of order 8 that you give me will be isomorphic to one of these. Okay? Maybe we can prove that. We'll prove that maybe in another review session. We'll prove that. Anyways, let's not worry about it. Okay, why is Z8 and Z4 plus Z2 not isomorphic? What does order of the elements? Very good. So what is the maximal order of Z8? An element, maximal order of an element is 8. Now what's the maximal order of an element here? 4. Here? 2. Very good. Now, the maximal order of an element, 8, 4, 2. So these are not isomorphic. Now these 3, can any of these 3 be isomorphic to any of these 2? Why? A billion, exactly. These are a billion here. A billion. And a billion. Not a billion. Not a billion, right? Agree or not? Yes. So none of these is isomorphic to, so if you pick anyone from here, anyone from these 2, they won't be isomorphic, right? Because those are a billion and those are not a billion. If you pick any of these 2 from here, any 2 from here, they will not be isomorphic. Because the maximal order of an element is 8. You can find an element of order 8. You can find an element of order 4, namely 1, 0, right? Has order 4. Here you can find the maximal order is 2. Okay. Now, why in D4 and Q8 are not isomorphic? I mean, D4 has an element of order 4, and Q8 has an element of order 4. Of course, they don't have elements of order 8 because they're not abelian. Right? If they had an element of order 8, then that would be cyclic because these have size 8, right? Now, what's the feature here? How many elements of order 2 does D4 have? Or Q8, how many elements of order 2 does Q8 have? Of order 2.
6.
So let's count. So I have 1. I have -1. No, Q8, no. Yes, you mean 6 of order 4? Oh, yeah, you have 6 elements of order 4, 1 of order 1, and what as well? How many? So you have 1 minus 1, I, j, k, where I squared, j squared, k squared is equal to -1. What are the orders of I, j, and k? 4, right? Minus I, minus j, minus k have order 4 as well. So what is the only element of order 4 in Q8? Of order 2, sorry, in Q8? Minus 1, right? One element of order 2. Which is -1. Now D4, how many elements of order 2 do you have? Look at look at the reflections of the square. So how many reflections do you have? 4 reflections, and the reflection has order 2. So you have at least 4 elements of order 2. And you have 5 because you have the rotation squared. Exactly. So at least 4 elements of order 2. Back. Okay, you see that? You have the 4 reflection and the rotation squared. All of these are the elements of order 2. So are these isomorphic? No. Okay, is that clear?
So none of them are isomorphic.
No, yeah. Because in everyone, so the first and the second, are they isomorphic? No, because the largest order is 8, and the element of maximal, or the maximal order of an element is 4 in the second one, but they're not isomorphic. Yes, of course, because 2 cyclic groups, that's an important point. And if you have 2 cyclic groups of the same order, then they are isomorphic, right? This is the privilege arrangement here, right? Well, this is the, well, yeah. Okay, any questions on this? So if I tell you, write down, I don't know, non-isomorphic groups of order, any given order, you can find. Well, not any given. Prime, you can only write one, right? If I give you how many groups of order 5 you have up to isomorphism, you have only one, because any group of prime order is cyclic, right? Yeah. Okay. Any questions? Yeah.
Wait, a cyclic group doesn't have to have a prime.
No. The converse is not true. Right? If you have a cyclic group, it doesn't have to have prime order, because you can have a cyclic group of every given order.
Yeah.
Z mod NZ, exactly. Z mod 2, Z mod 2, Z mod 3, Z mod 4, Z mod 5, Z mod 6, Z mod 7. All of these are cyclic. But if you have a group of prime order, it must be cyclic. Pardon? How come? So take a non-identity element. Its order will divide P.
Yeah.
So if it's non-identity and has order dividing P, so it must have order P.
Exactly.
So the group must be cyclic.
Can't it just be a group with order P?
Yeah, but I mean, let's write that. So let P be a prime.
Because for it to be cyclic, it has to be generated by one element.
Exactly.
How do we know it? Oh, because it's because
The
it's
side matches.
Yeah.
Exactly. Different. So P prime, G group, and G has size P, and G is cyclic. Okay, why is that? So pick G and G. G different than the identity in G. G will be the identity in G, since P is prime. And G is different than the identity. Then G has order P. and the subgroup generated by G has size P. Now you know the subgroup generated by G is a subgroup of G. So G is equal to G. Okay. This has size P. So
is it worth learning the proof of the Chinese or the Chinese?
yes, definitely. Definitely. I mean, we'll see another proof tomorrow. For rings, we'll see a more general proof tomorrow for rings. So these are as groups, and these are for rings. Yeah. I mean, the Chinese remainder theorem for groups, I mean, what did we use? We just used that one n and one m has order LCM mn, right? And then if mn are coprime, then LCM mn is equal to mn, right? And then you have an element of order mn in a group of order mn. So this group must be safe, and hence isomorphic to Z mod mn. We didn't explicitly construct an isomorphism. Okay, great. Now, okay. Should I write these down or they're good here? You can like listen to them again if you want. Should I write them down or? Okay. Great. Now the first isomorphism theorem. Let grow from G to H group homomorphism. Homomorphism. And G modulo per row is isomorphic to row of G. You have to know the proof of the statement, the proof, and applications. Okay.
I have a question for the last two because they don't have the same structure.
Well, because they have different number of elements of order 2. This one has 5 elements of order 2, and the other one has exactly 1 element of order 2. You could do 4. Yeah, we could do 4. So this one has, you just have to find one feature that is not in the other. Okay. Great. Okay, proof and applications. The proof of the first isomorphism theorem. It has many steps. You define a homomorphism from G mod row, which is a well-defined group because the kernel is a normal subgroup that sends a coset G to a row of G. Right. This is the first step. And what you have to show that this homomorphism is first before when you're well-defined because you're working on cosets. You need to show that this doesn't depend on the representative of the coset. You show it's well-defined and injective. You can do well-defined and injective almost in the same steps by just chain of equivalence. And then you show it's surjective. And then boom. Okay? Yeah, you win. Okay? Yeah.
G's row and phi interchangeably like.
I mean, you know, whatever. Phi can be a group homomorphism, row can be a group homomorphism. I can call it T, I can call it S. Okay, any questions? Proof and application. I mean, you've seen application in the homeworks, right? Find homomorphisms between 2 cyclic groups. Find what as well. Find, yeah, if I have a group of order 2k, for example, where k is odd, then you can find a normal subgroup of index 2 if G is a finite group. This is in the bonus homework. Yeah, remember this in the bonus homework? Well, I do. So please try to have a look at that. And okay, so any questions on this part? You just have to know how to prove the first isomorphism theorem and apply it. Okay, you can easily get questions that are very short, just applying the first isomorphism theorem. Okay, any more questions? Yeah.
If rho is surjective, we can 0 is just H, right?
Pardon me?
If rho is surjective.
Yeah.
Rho G.
Yeah, exactly. If rho is surjective, then rho G is a H. Exactly.
So if rho J is H, is surjective.
Exactly. If and only if rho G is by definition. Doesn't have to be a homomorphism. Any definition. Okay. Great. Are we good here? Okay. So great. Now we'll move on to more important stuff. The part that is very important. What is it? Group action. Okay.
80% of the exam, right?
What do you mean?
80% of the final.
No, not 80%. Definitely not.
You said you could answer.
No, I mean rings. Well, so groups. So groups will be 4 on 7. 4 questions on 7 will be on groups. Out of these 4, I say 3 on 4 could be answered with group actions. 3, 2.75 on 4, 2.9 on 4 could be answered with group actions. Okay. Yeah.
What about the second and third?
Don't worry about it. Okay. Don't worry about it. I even forgot what's the second. Yeah, so it's H modulo H intersecting again. Okay. So let's not worry about the second and the third isomorphism theorem. Okay. You'll see. Okay. You'll see. But I mean, is it an induction question like 1 plus 2 plus n is equal to n times n plus 1 over 2? No, you won't have that. Okay. Great. Anyways, now let's move on to the very important part. I mean, before just, I mean, I'll also do a recap from the homework. Or, like we have seen some fact of the homework. So if G is a group, H, K are subgroups of G, and K is normal of G, then HK is a subgroup of G. Then HK is a subgroup of G. And HK has sides H, K, H intersection K. Okay. You don't have to know the proof of that. You just have to know the statement. Yes.
What about Bailey's theorem?
Yeah, that's correct. That's
Okay.
correct. Okay, this is what you have to know.
So
Okay.
not the proof, just
You
the
don't have to know the
statement.
proof. No. And then you just have to know that HK in that case is equal to KH. I won't ask you for the proof. I mean, these are more, it's used in a proof of something, for example, but I won't ask you the proof. And basically, if you ask me to write down a proof for the second statement, I'll just look at it for like 2-3 minutes before I start. So it's okay. So just the statement, not the proof. Yeah. Yeah. Yeah, I've seen in class or in the homework or whatever. Yes, I'll trust you that you have seen it in class. Okay? I know that you have seen this in the homework or in class or whatever. Okay, so HK is a subgroup of G. Now you know the reason I introduced it is because this is used in the second isomorphism theorem, right? And then I say, okay, since I introduced it in class, let's give it in homeworks, and it turns out to be a very useful. Very useful equalities to work with, especially in classifying group. Anyways, right now. And then maybe one more. So if H and K are normal, let's say, right? And H intersection K is the identity in G, then HK is isomorphic to H times K. Right? You remember this? I mean, maybe I said that if G is equal to HK as well, then G is isomorphic HK. Maybe we've seen it this way, right? Yeah, we've seen it this way. Yeah, that's the way you should. Okay. And yeah, you remember that? This is homework 7. Homework, I don't know. I don't know what homework, but it's in a homework. Homework 8, maybe. Yeah. Okay, this is a useful one. Okay, great. Pardon me?
We should.
No, 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 no,
The
no.
same
I
thing
won't
as-
ask you for the proof of this. You can rest assured, yeah, that I won't ask you for the proof of these. Well, I don't know. I don't know what they're called. Okay, so but you just can use them. Okay, so you can use them. I won't ask you for the proof. Okay, it's a bit reassuring because I mean the proofs are a bit technical, right? So it's I won't ask you. You can just use them. Maybe you won't need it, but maybe you will need it. So, I mean, but you're allowed to use them. In case you need them, you're allowed to use them without proof. But you're encouraged to use them without proof. Because if you prove you might miss a step or something, then it's a problem. But okay, very good. Now, what do we do? Cayley's theorem. Very important proof. Very, very important. What time is it?
6:48.
So now, our Cayley's theorem. What do you have to do with Cayley's theorem? Statement. You want me to restate it, or that's good?
Can you?
Yeah. So then give me a group. Then G is isomorphic to a subgroup of sim G. Okay. You should know how to prove it. I can ask you. You can assume something, and then and then use it. Do you want to rewrite the proof, or that's okay? That's okay. Okay. Great. You should know how to prove it, and use it. Okay. So I think in the bonus homework 7. You use it for something. You express if you have a group of order 2k, then you found, and where k is odd, then you showed that G must have a subgroup of order k as the kernel of a homomorphism. Okay? You remember this question? Yeah. Okay, I mean, okay, so maybe I'll write it down. I mean, some questions that could appear. These are, a repeat of homework questions. So, I mean, how you prove Cayley's theorem? You take lambda G from G to G, and you send X to GX. You show that lambda G belongs to sim G, and rho from G to sim G. In a sense, G to lambda G is injective. This, how you do it by Cayley's theorem. And then you can apply it. For example, if G is equal to N times M, and G has order N, and lambda G is a product of M disjoint N cycles, right? So it's N cycles of length N. You remember this? You take the right cosets of the subgroup generated by G, and you see how lambda G is. Okay? This is homework 7. Okay. Okay, these are important things. But let's move on. There are things that are more important. Okay. Any questions from the people online? Okay. Great. Now where should we move? This is the most important part. Group actions of sets. Or maybe maybe there's something as well very important. On group homomorphism, but I will say it later. That's okay. Group action of sets. So first, And you have to know to define an action. Define an action. It's a function from G cross S to S, satisfying blah blah blah, right? Define the orbit orb S and stab S. Okay. Show stab S is a subgroup of G, right? Show that stab S is a subgroup of G. What as well? That two orbits that S is a disjoint union of orbits. How do you do that? So what do? You define an equivalence relation, right, on S. Interpret orbits as equivalent classes of the following relation. S1 is related to S2, and only if there exists G in G such that G star S1 is equal to S2, right? To show it's an equivalence relation, the orbits are the equivalence classes, and very good, you get that. Now the most important one is orbit stabilizer theorem. Orbit stabilizer theorem. You have to know that. Okay, so people don't have questions. The people attending in the lecture virtually. No. Okay. Orbit stabilizer theorem. What is it? You have a bijection from G step S. And what is the bijection? We send the coset G step S to what? To G star S. How many steps you have to show here? Well-defined, injective, surjective. Okay, well-defined and injective, you can do them by chain of equivalence. That's okay. And then you have to show it's surjective, which is obvious. Okay, great. Are we good here? Yeah, you have to show this. You have to be able to show this. I can tell you, state and prove the orbit stabilizer theorem, or any of these. State and prove. So, for example, show that stab S is a subgroup of S. Define the stabilizer of S and show it's a subgroup of G, sorry, not of S. Okay?
Yeah, I think you get a question exactly like that, but you forgot how to prove that, but you remember how to prove the orbit stabilizer theorem, you still get
Zero. No. I mean, if you don't answer the question, you get 0. Of course, if you don't answer the question, of course, it's 0. Otherwise, you can do that for every question, right? Pardon me? No. I mean, you have to answer the question, right? If you go outside the way, then of course 0. I don't think you get any marks in any other class if you're right. Things like that. Okay, great. Now let's. So these are very important. You should not use these. Now, what's an important thing as well? Where did we apply this? We applied this to P groups, right? Before we applied this to P groups, right? The P groups. Or let's some important group actions. G acts on G by conjugation. Right? You remember this? G acts on the cell by conjugation. So you take a function from G to G, G cross G to G. You take G and X, and you get back G X G inverse. You need to show this a group action. Show star an action. Now, what are the equivalent? What are the orbits called in this case? Conjugacy. What? Classes. Very good. So the orbits are called conjugacy classes. Conjugacy classes.
That looks a lot like the definition of a normal subgroup, if you know what I mean. Like, you know,
Yeah, I mean, yeah, we'll see another example. Yeah, of course. I mean, G will act on a normal subgroup as well in the same way. Right?
yeah.
Exactly. G X G inverse. Exactly. So show star is an action. Now, what is the set of fixed points here? Set of fixed points. Set of fixed points or set of orbits of size 1. What is this? What are the elements that are fixed by this action? Gx G inverse is equal to X, right? For all G and G means that if and only if X belongs to the center of G, right? So what is fixed point is the set of orbits of size 1. So Gx G inverse is equal to X for all G and G, if and only if X belongs to ZG, right? Agree or not? Yeah, we've seen that. So the set of fixed points of this action is ZG. And then you get that if G is finite, then G is equal to ZG plus the sum, let's say from I equal 1 to N G stab Xi, and what is the stabilizer of an element X? Stab with X. Right. Stab with X here is the centralizer of X, right? G CXI, where X1 up to Xn are representative of non-singleton classes. Agree or not? Yeah, remember that? This is an equation we derived. People online, please don't hesitate to ask questions. Okay, this is very important. Okay? You remember this or not? We derived this in class and in the homework. Now, what's another group action that we have seen? Or that you have seen in the homework? If H is a normal subgroup of G, if H is a normal subgroup of G, right? Then G acts on H by conjugation. G cross H to H, that sends GH the inverse. This is G star H in that case, right? And why does GH G inverse belongs to H? Why does it belong to H? Anyone can help me? Because H is normal. H is normal, and you have to justify that if you get a question like that. So GH G inverse belongs to G for all belongs to H, sorry, for all G and G H. You have to show this is a group action. You have to show that star is a group action, right? Show it's a group action. Sorry, just I'll finish this one. Star an action. And what is the set of fixed points in that case? What is the set of fixed points? So it must be a subset of H, yes. But what is the set of fixed points? You've done this question on the homework. I'm pretty sure you've done that. What is the set of fixed points? Write down the set of fixed points. G inverse is equal to, H is fixed if and only if G inverse is equal to H, right? For all G and G. If and only if GH is equal to HG for all G and G. If and only if H belongs to ZG, right? So what is the set of fixed point? It's H intersection ZG, right? Okay, these are very important. Okay, these two are very important. Okay, these two are very, very important. Okay, are we good here? I mean, it's recorded, so you don't have to take pictures. Oh, okay. You want to write it? Yeah. Okay. Okay. So these are very. Pardon me. Fixed point is orbit of size 1. What does fixed point mean? It's an element of the set such that star S is equal to S for all G and G.
And so the orbit.
The orbit is a singleton. Exactly. Orbit of size 1 or fixed points. Are we good here? Yeah. Well, yeah, you can use it unless I tell you show it. Okay. If I tell you show this, you cannot say it's in the homework. Okay. If I ask you that, you cannot just say it's in the homework. Okay. And these are solved, like I think, in an exercise session. Right? Anybody who attended, I think I solved this in an exercise session. I did these in an exercise session. Yes, you remember? No, you don't. Okay. Anyways. Yeah.
So G is essentially the identity, but it doesn't change anything.
Well, any G will act as the identity. G is not the identity, but will act like the identity.
How does it do that?
Pick any element that is in the center, right? Pick the identity for S, and that actually says pick the identity for S. G star the identity is the identity. Okay, so the identity is a fixed point. Okay?
When G star the identity, G.
No, G star the identity is the identity in that case. G star the identity, because your identity is an element on the set. H is a G set here. The G set is H. Okay?
So is G the singleton or is it S the singleton?
No, S, an orbit, right? Orbit. Right? Yeah, the orbit. Yeah. Oh, centralizer is the set of elements in G that commute with X. ZG, so GG is the set of elements that commute with everything. Okay, so CX is just the element that commute with X. ZG is the set of elements that commute with everything. Okay? Okay? Great. Awesome. Okay, these are very important. Remember these. Please remember these two actions. They're very, very important. Okay? Anyways, they're very important. Okay?
Why is it not just ZG?
Because ZG, you might have, it's a subset of H, right? So the set of fixed points is a subset of H. But it must be H intersects in ZG. Right? I mean, ZG could intersect things outside H as well. Could contain things other than H. So it's a subset of H. It's all the elements of H that are in ZG. Okay? Is that clear? Are we good? Okay, so please know these two actions. They're important. Now we have two very important, I mean, everything, yeah, I'm saying everything that I did, but two important actions. What is the important action? G on the set of cosets, right? G on G mod H. This is the Most important. Yeah, third important action. G acts on G mod H. If H is a subgroup of G. So what is the action? You have to show, if I ask you to show that this is an action, you have to be able to show, right? G, so how you define G star XH is just GXH, right? You remember this? This is the most important action. Like you will have a question on that. There is no no debate. You know, you will have a question on this action. Okay, so everybody, you can just start writing. You can just oh, hello from Algebra 3. Okay. Great. You can just somebody wrote the chat. Yeah. You. So someone is in Algebra 3. Okay, so this action, you will have a question on it. Okay, you will. What is this action? What is the homomorphism of this action called? What did we call it in class? Cosine. Oh, very good, very good. That looks good. Okay, what is the stabilizer of a point XH? So what is the stabilizer? I mean, let's take the stabilizer of H. What is that? What is the stabilizer of H? It's just G and G, such that G H is equal to H. What is that? Yeah, say. Don't hesitate. Say out loud. H. Very good. Now, what is the stabilizer of XH? Say, yeah. Don't hesitate. Even it's strong. That's okay.
Well, it's the one where you did the intersection, so it's like different.
Yeah, exactly. But before that, what is it? It's a subgroup. So yeah, say XH X inverse. Very good. Okay, you have to derive these. You have to know how to derive these. And you derive these in a very simple way. Okay, in general, if you have a group action, then stab G star S is equal to G stab S G inverse. Okay, great. You have to know this action by heart. You know how to derive it, know how to find the stabilizer and everything, and know how to apply it. Okay, any questions? Samuel, did you have any question? No? Okay. Great. Stab G star S is G stab S G inverse. Okay, great. What we have one more action that we focused on. What is that? Anybody? Anybody? We have one more. Let's remember the seal of theorems. Yeah, but what is the action here? What is the action that we? It's it's a transitive action, yeah, but what is it?
Lattice theorem.
The?
Lattice theorem.
I never said that word. Did I say that word? I don't think I did. I ever did. What is the most important action? One of the most important actions. This is the one, but there's one that is also important. What is it? C.
Conjugate clauses.
Well, conjugacy classes. Conjugates very good, but on we applied it to elements, right?
These subgroups
But let's forget about the piece that in general. Let's not like read and say things. But what is it? What is the action that is important? If I have a subgroup, what can I do with a subgroup? I can conjugate elements, and then I can conjugate subgroups. XH X inverse. If H is a subgroup, then XH X inverse is a subgroup of G. You remember that? And then we use the fact that G acts on this set. A very important action. G acts on the set X, H, and inverse, and that is in G. Let's call this one S. G star S to S. What is that here? I take an element G and I take the star of times here, X, H, X inverse. What do I get? What should it give back to me?
X inverse G inverse.
Very good. So we've seen this actually before, right? We've seen this one before. Yeah. So what can I say about, this action, what can I say about it? This is also transitive, right? This action is transitive. What does transitive mean? You should be able to tell me what transitive is. Yeah.
X raised to Y are related to X raised to Z.
What is
No.
what is related? Is it? Yeah, sure. But what is related in that case?
Oh,
Related is being. Hit being. You can reach it from G, right? G star something. Very good. So it means that how many orbits you have? You have only one orbit, which is the set S. Okay. This action is transitive. It's transitive. What is the orbit of H in that case? The orbit of H is just G star H as G is in G, which is just the set GH as G is in G, well, which is just G1H, the set of left coset. In that case, this is a transitive action, right? Is it clear that GX, X inverse, G inverse belongs to S? It's clear, right? Because this is just GXH, X inverse, G inverse. GX, H, GX inverse, which belongs to S clearly. Okay? This action is transitive. Because what is the orbit of H in this action? This is just GH, G inverse, as G belongs to G, it's just S. Agree or not? If you're confused, ask. This is the place to ask. Yeah.
What is that say?
Wait. Belongs to S. Belongs to S.
Is it G?
Oh, I just put GX. I just put this. I just put them so that I write it in this way. Okay? I just showed that it. That was clear? Yeah. And this belongs to S. Why does this belong to S? Because you can write it as an element of G times H times the same element inverse. Yeah.
So what's the stuff you're writing?
Group actions. Exactly.
Yeah, but like was that related to that group action?
Yeah, of course, that group action. What is
Okay, that's
yeah? What is the orbit of H in that case? What is star in that case? It's G times H, right?
okay. I just need to
Yeah. Is it clear now?
Yeah.
It's GH as G is in G. What is star in that case is just GH inverse as G is in G. Okay, which is X. So those actions are transitive. What is the stabilizer of H in that case? It's the G in G. What is G star H in that case? G star H in that case, definition, what is it? GH G inverse is equal to what? Equal to H. What we had the name for this one? What is the name for this one? We had a name for this one. N starts with N. Normalizer of H and G. Right? So a good trick here, if I tell you show something is a subgroup, express it as the stabilizer of a group action. Okay? Now these are the most important actions. Do you mind shifting the camera slightly? Is that better? I brought it a bit forward. Yes, the right board is not visible. That's because of me. Now, is that good? Is that good? The right corner is not visible? Really? Okay. Because I can see it here. Oh, okay. You mean it's a bit blurry. Okay. I think orbit of H. Oh, so the orbit of H is G star H as G is in G, which is GH which is as G is in G, which is G mod H. Okay, great. Are we good? Is that the only part that is not visible? KL? Everything else is good, right? Okay, okay. I'll just rewrite it. So it says that the orbit of, it's the orbit of H is just G mod H. So this is just G star H as G is in G, which is GH as G is in G, which is just G mod H. Okay, so these are the most important actions. Yeah. Actions of G on the conjugates of H. I think we called it this way. I don't know what we called it, but yeah. Okay. It's in the homework. It's very important. Okay, so these 4 actions are very, very, very important. So you will have a question on G acting on G mod H. That's there is no doubt on that. So you have a question on that. Okay, and you may or may not have a question on one of the others or more than one of the others. Yeah. Okay, are we good, guys? Yeah.
Can you explain a little more the last thing you said? Express a subgroup as a stab of a group.
Yeah, so if I tell you show that the normalizer of G and H is a subgroup, instead of going through the axioms of this, you can tell me, well, for example, but that should come more in a problem. But anyways, if I tell you show that G acts on this group, and you show it's a group action, okay? And then the next step, I tell you, show that the normalizer of H in G is a subgroup of G. Instead of checking the axioms one by one, which is not very hard, but you can tell me, oh, it's a stabilizer of an element, and you know the stabilizer is subgroup, so you win immediately. Okay? Are we good? So if I tell you H has 5 conjugates, the conjugates of H are 5, including itself. What is the index of the stabilizer? By the orbit stabilizer theorem. What is the index of the normalizer? G and GH is equal to the orbits, right? The size of the orbit of H. If I tell you that H has 5 conjugates including themselves, how many orbits you have here? How many elements you have in S? If H has 5 conjugates, if this set has, basically this set has 5 elements, right? What is the index of the normalizer? 5, right? And we use this in the proof of Seelo's third theorem. You remember? Yeah. Okay, great. Now, this is an important part. You should be very confident with these actions. Okay, very, very confident, and be able to Oh, so yeah, very good question. Why do we care about the orbit of H and not the orbit of a random XH X inverse? So if you manage to show that the orbit of H is the entire thing, then the orbit of XH X inverse is the entire thing. Okay? In that case, because you can guess that the action is transitive. Okay, great. Are we good here? Okay, now a very important part as well. What's a very important part? Group actions in use. Homomorphisms. So let G. Let S be a set. And well, then there exists a homomorphism. So please, homework 7 and 8 are very important. 7, 8 for groups are really important. Okay, you should master them totally. Totally. Like you should be in total command of homework 7 and 8 of these type of questions. Okay. And the bonus. 7 is the bonus. 8 and 9, like the questions that do not involve a lot of Seelo theorems. I mean, suppose I tell you, so you should be able to do the questions, even if you don't need to use the Seelo theorems. Okay. So if I tell you, suppose that G has a subgroup of that order, for example. Okay. Anyways, you should know how to do the questions. Okay. You will not get something really hard, but you should know the group action questions 7, 8, 9. Please. Okay. They're very, very, very important. Yeah.
Two things. One thing, is it enough to learn these proofs of the group action?
No. If it's not enough. You should learn everything. You should be comfortable with any new action I give you.
Like applying.
Yeah, of course.
And lastly, I don't quite understand how you prove transitivity.
So take the orbit of H, show it's the entire set. So G star H is just GH for any G and G. For all G and G, this is the orbit of H, which is you can get any coset from H. Okay, so let S be as G said, then there exists a homomorphism rho, or then G said, then the action of G on S induces a homomorphism rho from G to the symmetric group of S, where you get G to lambda G, where lambda G is the function from S to S, defined by G star S. So first, we need to show that lambda G belongs to sim S, and that rho of G1, G2 is lambda G1, lambda G2. And what's the kernel of this homomorphism? It's the intersection of the. What is the kernel of the homomorphism? The intersection of the stabilizers, right? Remember this or not? Do we? No, we don't remember that. Should I rewrite it? It's a short one. So these, I think they're a bit long, so I'll let you relook at the notes. Yeah, so the kernel of rho. So X belongs to the kernel of rho if and only if lambda X is the identity on S, if and only if. What does the identity on S means? X star S is equal to S for all S in S, right? If and only if X belongs to stab S for all S in S, if and only if X belongs to the intersection as S is in S of stab S, right? Is that clear? That should be clear, right? This should be clear, no? Yeah, these are clear. Are these chain of equivalences clear? Are we good? Are we good with this? This is important. You might, you might get a question on this, or I might ask you, rewrite this. Show that the action of rho on G induces a homomorphism from G to sim S, or I might not, but but I mean, it's very important. So I mean, if it makes you feel more confident, you will get a question. Group action will induce a homomorphism. What is it? You'll figure out, but you will have a question like that. Okay? Group action inducing a homomorphism. We did many examples of this, right?
So it's going to be something that we've seen before.
You'll see. Okay? You'll see. You'll see if you've seen it before or not. But again, it should not be something extraordinary. Okay? Yeah. I had a good one, but I figure out it's a bit hard. Sorry. It's an original one. It's a two-liner, but it was a bit hard. Maybe I'll give it as practice. We'll see. Okay, great. Let's move on. Now, from this, what should you be able to derive? The coset representation, right? Let G act on G mod S. Act on G mod H is a subgroup of G. H is a subgroup of G. Of course, here you have another exercise that I can give. It's from the homework, right? So if you take homework 8, if rho is a homomorphism from G to sim S, then you have an action of G on sim S. Then G star S, which is equal to rho G S, is an action. Okay, see homework 8. Very important also. Okay. Homework 8, question 2 or question 1 maybe, right? I think. Are these homework 8, question 1 and question 2? I can't remember. Okay, but so let G act on G mod H. What is the action of G on G mod H? G XH. I send it to G star XH. What is this action? How do I define it to be? Everyone? Everyone? What is it? GXH. Very good. GXH star induces a homomorphism rho from G to sim G mod H. And what is the kernel of rho? Kernel of rho is the intersection of the stabilizers, right? What is the stabilizer of an element XH in that case? XH, X inverse, very good. As X is in G, right? Remember this or not? I derived this in class, so please know how to derive this, okay? Know how to rederive this, because I might ask you. No questions from the people in attending online? Anyone? No questions, great. Okay, great. Now what's a very important one? If H has index n, n and G, then what can I say? The action. I'm writing it because it's important, of G. When G with H induces a homomorphism. Rho from G to a symmetric group on G mod H, which is isomorphic to Sn, and curve and N, which is equal to curve rho X in G, X H X inverse, then G mod N is isomorphic to a subgroup of Sn by the first isomorphism theorem. Of course, then N is contained in H. Of course, here the kernel is contained in H, right? And N is contained in H, and G mod N isomorphic to a subgroup Sn. In particular, what is the index of G mod N divides n factorial, and N divides the index of G mod N. Do you agree with this or not? N divides the index of G of N and G. Why is that? Because N is contained in H, is contained in G, so G H, so N G H divides G. Okay, that you should be very comfortable with, please. Okay, if you get a question like that, it should not be surprising. Yeah.
When you say like the derive the coset representation, what is like?
I'll limit your judgment. I mean, usually this Yeah, I don't want you to.
Whether it's isomorphic to.
Here, I just want you to start here. Okay. I don't want you to write the whole group action business. Okay. Just redirect the kernel. Show me that the kernel is XH X inverse.
But I just had like the final thing, this showing.
Yeah, usually this is okay. You can say that unless the like if I don't tell you to derive, let's say the action of G on the sets of coset of H will induce a homomorphism rho whose kernel is that thing contained in H such that blah blah blah. Okay, great. Now, if H is not normal, what can I say about N? Can N be equal to H? If H is not normal, for example, H is not normal in G, then N is different than H. The far right corner is very blurry. Yeah, sorry about that. I mean, I'm usually saying what I'm writing. So here, what I say is, if H is not normal in G, then N is different than H. Okay, that's clear, right? Because N is a normal subgroup of G, right? N is the kernel, so it's a normal subgroup, and H is not. If H is not normal. Okay, is it clear or not? Now, where did we apply this question? What's an example where we applied that question? To find the a surjective homomorphism from what group to what group, for example? From? Say? In the homework, how many homework we did? From S4 to S3, very good. So we found that, and then you have the one in homework 9 also with the 96, the group of order 96. So basically, okay, so this coset business is very important. Now, why do I have a subgroup of order 8 in S4? What's a so example? Objective homomorphism. I think we did it a bit more generally. From S4 to S3. You remember that? We did it a bit more generally. If you have a group of order 24 and its CO2 subgroup is not normal, then you can find a homomorphism from S4 to S3, right? This is homework 8 as well. Now, how do we do that? Can you give me a subgroup of order 8 in S4? What's a subgroup of order 8 in S4? Sure, D4, but how do you want me to write it? How many copies of D4 can you find in S4? 3 copies of D4 in S4. Very good. I just know that. CELO theorems. Okay. So how do we write down D4? The square. Very good. What do you do? Yeah, you can do any labeling. 1, 2, 3, 4, and you look at the symmetries of this thing. Okay, we call them V, H, V1, and V2. What is V here? Oh shoot, okay, I shouldn't write H. Let's call little h little b, okay? I want to call my subgroup A, doesn't matter. Okay? What is H in that case? Anyone can help me. So, and you have the rotation, right? You have the identity and you have the rotation. So can anyone help me by writing the symmetries of this group? Who can help? Who volunteers? What is the symmetries of this set? When I ask you, write a subgroup of order 8 in S4, how did you do that in the homework? Other than ChatGPT? Yeah. Exactly. So yeah. So I have the identity first. I'll start with the first one. Anyone? R. So you say R. Yeah. What is R in that case? You're rotating everything by 90 degrees. So yeah. So where does 1 go to under R? Right. Where does 2 go to? Where does 3 go to? 4. Very good. Now, what do you have? If you have R, then you have R squared. What is R squared here? 1, 3, 2, 4. Very good. What is R cubed? 1, 4, 3, 2. Awesome. And then R4 is the identity. Okay. Now we have the 4 reflections. What are the reflections? Anyone can help?
1, 2, 3.
1, 2, yeah, 1, 1, 2, 3, of course, but how do you want to order them? So you're saying 1, 2, 3, 4, that, like that? Very good. 1, 2, 3, 4. This is the vertical reflection, right? Then I have the horizontal one. You agree or not? Is there any problem? Are we good? Is it clear? Yeah. So these are the symmetries of the square. Okay. You see how I'm writing them? So V is a vertical reflection. Reflect 1 around 2. What do you get? 1? No, this is 1. Reflected in V, what do you get? This is 4. V, this is the vertical. 1 to 2. Reflect 2, what do you get? 1, 1, 2. 3, 4. Reflect 3, what do you get? 4. 3. Now, help me with H, the horizontal one. How do you flip the horizontal? How do you reflect the horizontal one? And 4 goes 2. Very good. Am I done? Or I have one more. So 1 will go to 4 and 4 will go to 1. You have to determine the other 2 vertices. What happens to them? Horizontal. Horizontal. Under H. 2 will go to 3. And 3 will go to? Very good. Now let's look at diagonal reflection, D1. D1 is the reflection on this one. What will happen to 1? On this, if you have a reflection. It's not very good. 1 is fixed. What happens to 3? It's same. So what happens to 2? What happens to 4? Very good. Very good. Very good. Very good.
Up to 2 and 4 are fixed. 1 and 3.
1 and 3 are fixed.
But then
Under this reflection.
both diagonal.
No. D1. I'm saying the first diagonal.
Oh,
D1.
only that diagonal.
Exactly. Now what is D2? Anyone can help with D2? 1, 3. Very good. Let's explain a bit. What happens to 2 under D2? Look at D2. Belongs to D2. So when you reflect it, it stays fixed. 4 stays fixed. So what happens to D2 to D2? And what happens to 1? The 3 and 3 is fixed. I have my 8 elements. Are we good here? Okay? 100%? Is it clear? Yeah? Okay. Of course, you can choose any other labeling. Okay, I can tell you write down 3 copies of D4 and 8, right? You can relabel your square. Instead of 1, 2, 3, 4, you can write it as 1, 4, 2, 3. Okay? And then you find the symmetries of that figure, which is a square. Yes?
Where does the 1, 3, 2, 4 come?
Where?
The third term, 1, 3, 2, 4.
The third term here?
Yeah.
R, this is R, right? This is the rotation.
Yeah.
By 90. Rotate by 180. 1, what happens to 1 when you rotate by 180? 3, what happens? Goes back to 1. 2. Okay. Are we good with this? 100%. Should I give one more example to compute, or that's okay? Is that okay, everyone? Is that okay? Don't hesitate. Don't be shy. Ask. Yeah.
Where when you 1 does 180 goes to 3.
Yeah.
2 does 180 goes to 4.
Yeah.
4 does 180 goes to 2.
Yeah.
Is that why they're separated?
Exactly. 1 goes to 3 and 3 goes to 1. Very good. Yes, sir.
Is 1, 4, 2, 3, is that the same as 4, 1, 3, 2?
4, 1. No, 1, 4, 3, 2. So what do you say? It's 4. No, it's not the same as 4, 1, 3, 2. It's the same as 4, 3, 2, 1.
Okay.
Okay? It's the inverse of this one.
Oh, okay.
Okay? So this is the rotation this way. 90 this way.
Okay.
Is it clear?
Yeah.
Rotate by 90 this way. 1 goes to 4. 4 goes to 3. 3 goes to 2. 2 goes to 1. Okay? Or you can write it as 4, 3, 2, 1. Also. Is this stuff clear, everyone? 100%. Please be sure of calculations like that. I mean, we've done that 65 times in class, so it's important. Okay? Yeah, so please know how to do that. Okay, we've done this in class, we've done this last tutorial, we've done this in the homework 5 times. Okay? So please know to do this. Great. Now, is H normal in S4? Why is H not normal in S4? Julian, 4 different ways. No, you can label it in three ways. So yeah, you can relabel it in 3 ways. You can relabel it in 3 ways. So let's say 1, 2, 3, 4. Then what do you have? You have 1, 4, 2, 3. This is different. And then so I have 1, 2, 3, 4. Here I have 1, 3, 2, 4. So I have 1, 2, and then I have 1, 4, 2, 3. These are the 3 ways. Okay. You can relabel your square. Any other way is the same. Now, if you want a good way to relabel the square, always you want the rotation squared to be 2, 2. 2 cycle, 2 cycle. So choose your pair, 1, 4, and 2, 3. Okay, you have 3 ways. Okay, Julian, is that good? Is it clear? Thanks. Okay, thank you. Okay, are we good? Okay. Okay, now this gives me, is H normal in S4 or not? No, why is H not normal? And yeah, take it. Very good. So let's do that. Let's pick an element. 1, 2. Is it in H? No, so it's a good try. I start with that. Let's pick an element in H. 1, 2. Oh, okay. And then why 1, 2? Okay, 1, 2 inverse. What is 1, 2 inverse equal to? Okay, 1 goes. So what is the size of this? What should I get? I'll get a transposition, right? Because when you conjugate the cycle of length n, you'll get a cycle of length n. Great. What is that? 1 goes to 2, 2 is fixed. So 2 goes to 1, so 1 is fixed. 2 goes to 1, 1 goes to 3, so 2 goes to 3, and 3 is fixed. 2 goes to 3. Okay, does it belong to H? Doesn't belong to H. So H is not normal.
It's in H. 1, 4, 2, 3.
No, 2, 3.
Oh, by itself, by itself.
Yeah. So H is not normal. So the action S4 of S4 on S4 mod H induces a homomorphism from S4 to the symmetric group of S4 mod H that is isomorphic to S3. Let's call it rho, 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 rho. From S4 to S3, such that the kernel of rho is the intersection of the conjugates of S4. Now, is the kernel of rho contained in H or not? Is the kernel of rho equal to H or not? Can the kernel of rho be equal to H? Why?
H is an X.
H is? Yeah, and the kernel is normal. The kernel is contained in H. Okay, since people cannot see, I'll write here. Can I erase this stuff? Can I erase it? Now, rho is different than H. Since H is not normal in S4. Now, what can I say about the index of rho? The index of rho is strictly bigger than the index of H in that case, right? We agree or not? Because were they equal, then H would be equal to rho, right? Or not? Yes or no? And what can I say about the index of rho? The index of rho is what? Divides what? N divides the index of rho. What it divides? The size of S3, which is n factorial, right? Are we good? Are we good or not? G mod curl divides 3 factorial equal the size of S3. Why is that? Since G mod curl is isomorphic rho G, a subgroup of S3. So the size of G mod curl divides 3 factorial. Agree so far or not? Everybody, we agree? 100%. So G mod curl divides 6 and is bigger than 3. What is the index of H in that case? 3, right? Because H has order 8, S4, G is S4. Whenever I write G here, is S4. Okay? Agree, everybody? Do we agree or not? Any questions on that? Ask, don't hesitate, ask. Yeah. The intersection of the conjugates of H. So if an element belongs to the kernel, then it belongs to all the conjugates of H, agree? Now H is a conjugate of itself. Put X equal to the identity. Is it clear? 100%? Are we good here or not? So G mod curl divides is bigger than 3 because H, what is the index of H in S4? 3. Why is that? What is the order of H? 8. What is the order of S4? Are we good here or not? Yeah? Okay. Great. So, yeah, so G mod curl divides 6, and G mod curl is strictly bigger than 3. What is G mod curl? What is the size of G mod curl? 6. So G mod curl has size.
But how curl is the identity?
No, not necessarily. No, in fact, it cannot be the identity. Because if it were the identity, you would have an injective homomorphism from S4 to S3, and that's not possible because S4 has more element than S3.
I thought the whole point
It masks the identity, but it's not necessarily the identity. Okay, kernel is not the identity in S3, in S4. Sorry, you could have more elements in kernel. In fact, you have more elements in kernel.
So the kernel maps its identity. What is it itself?
It's a normal subgroup.
Okay.
In that case, it's this one. Now we'll see what it is in that case. So if are we clear here? 100%. Ask if you don't ask if there's something you want me to explain. Ask. Don't hesitate. Yeah.
Can we just go through it was
Yeah. So what is the size of H that I found? Okay. What is the size of S4? What is the index? How many left cosets do you have? Over.
it's going for
Is that clear?
Yeah.
Yeah.
We know that the index of G is bigger because it's smaller.
No, it's in fact it's usually bigger or equal, but since H is different than kernel, it's strictly bigger. Do you want me to explain why? Yeah. Okay. So you have H is contained in S4, and H is contained in O. Okay. All of these, so you can define in the indices the index because all of these are subgroups of each other. Okay. So S4 divided by H, we're working with finite groups. This is just S4, sorry, divided by kernel. It is 4 divided by H times H divided by rho. Agree? Yes, rho. Okay. Now, the index of S4 and H, if these two are equal, then rho would be equal to H. But this is not possible since H is not normal in S4. Is that clear? You think so, or do you want me to repeat it? I could repeat it.
Yeah, what is it?
So you agree with this?
Yeah.
Exactly. So the index of S4, this gives you that the index of S4 in curve row is bigger or equal, in fact, divisible by the index of S4 in H. Agreed? Because this is bigger or equal to 1. Right? Now, it's equal if and only if this is equal to 1. And this is equal to 1 if and only if curve row is equal to H. Because curve row is a, okay? Now we know that curve row is different than H because curve row is normal and H is not. So this thing here is bigger than 1. So this thing must be strictly bigger than the index. Clear? No problem. Is that clear, everyone? Please make sure it's clear. If you have questions, please ask. Yeah.
It's bigger.
Strictly bigger.
What's that?
Numbers.
It's like the number of like sets.
Yeah.
So there's more of them.
Because S4 mod the curve of row, you can write it this way, right? So this tells you that S4, the index of kernel of row, is at least the index of H. Okay? Now it's equal to the index of H if and only if this thing is 1. If the index of curve row in H is 1. The kernel of row is equal to H, but you know the kernel of row is different than H.
Therefore contradiction.
Yeah, exactly. If you're assuming equality. Exactly. Are we good here or not? 100%?
Is it that the index of curve row is smaller than H?
No. No, the index of curve row is bigger or equal to the index of H. The size of curve row is smaller than H. Yeah, the size of curve row is smaller than H. So we take 1 over, exactly, very good. So when you take the 1 over sizes, then you get it here. Are we clear here or not? Any questions on that? Okay, great. Yeah. Practice, I mean, you have the homework. I'll give you like 5 variations of that. Okay. But is it clear or not? Do you want me to post a practice final? I could post one. Okay. Or I could post a practice final, but I'll just make it too hard. Okay, so it won't be represented. I'll just make it too hard so that you mint so that because the practice final was too easy. This is the usual thing. So if I post it and it's too hard, then I don't think that. But if you want, I can post practice questions. Sure. Okay, is that clear? Yeah. Okay, but we can finish this one. Okay, any questions on this anymore? So let's finish. Yeah.
Or you can, but what is the size of H?
Okay,
It isn't.
very good. Curve row is a subgroup of H. Okay. Suppose they have the same size. They're both finite sets. That's another proof. Very good. Very good. There's another proof. So, curve row is a subset of H. It's subsets, right? So curve row has size less or equal to H. Now you agree that curve row is different than H, right? Because curve row is normal and H is not. But curve row normal in G. H is not normal in G. So curve row is strictly less. That's way better actually. If you have two subsets if you have curve row is subset of H and curve row has the same size of H, they're both finite, and this means that curve row is equal to H. Right? So in that case, since H is different than curve row, then curve row, the size of curve row is strictly smaller than H. Okay, so the index of curve row is strictly bigger than the index of H. That is 3. Very good. Okay, now are we good here or not? So far, are we good? Everybody, are we good with this one? Yes or no? This we did in the homework. No, you remember or not? Okay, now S4, the index of the kernel in S4, what does it? It's bigger than 3 and it divides what? which is
Six.
6. S4 is bigger than 3. Sorry, the index of kernel of row. Right on. I mean, I can say a bit more. So, divide 6. And S4 of kernel strictly bigger than 3. What can I say about S4, the index of kernel in that case? Very good. So S4 is equal to 6. What can I say about row of S4 in that case? By the first isomorphism theorem, row of S4, what size does it have? So row of S4, which is isomorphic to S4 modulo the kernel. In that case, I'm talking about sizes, so they're equal. Has size. I agree with this part. This part we agree with, everyone? Yeah, we agree with. Agreed? Agreed? Row of S4. What? Yeah. Row of S4 is isomorphic to S4 mod per row, right? First isomorphism theorem. So these two have the same side. Agree or not? Now, what can I say about row of S4 in that case? Why is it S3? It has, so row of S4 is a subset of S3, let's say, and row of S4 is size 6. It's a subgroup of a row of S4 is equal to this. Or what did I use before? Anyways, what did I use? SimGH or S3 immediately? SimGH. Okay, so that's so isomorphic. Okay, isomorphic. Is so row S4. So row S4. Yeah. Let's write this. Let's just write this. Is that clear or not? Any questions on this? Is very important. This question you did like 5 times, right? I did like 5 times in 5 different ways. Sometime with the group of order 96 once, and 3-4 times with the group of order 24 with S4. And by the way, did anybody goes to Antoine's tutorial on Wednesday? He also did it a different way. Okay, so anyways, so row is surjective. Agree or not in that case? Because row of S4 is S3. The row is surjective. What is the size of the kernel of row? I tell you that S4 modulo the kernel of row is 4. Very good. S6. Is 6, right? So the size of kernel of row is what? 4. So kernel of row is that size. Now, in S4, I know the normal subgroups of S4. What are they? What is kernel of row? In that case, what is the kernel of row? What is it? D4 has size 8. V4. What is V4? What is Klein's group?
You showed it next.
Oh, I called the conjugates of H, H prime, and H double prime. Yeah, but okay, so what are they? How can I list them? Yeah, very good. I know the normal subgroup S4 has only one normal subgroup of size 4. We know this from homework 6. We derived it using the conjugacy classes, remember? Yeah? What do you want to call them? V4? You want to call it V4? We call it V4. V4? Although, sure. What is V4? Anyone can help me? Identity, very good. 1, 2 bracket 3, 4, very good. Then Very good. Thank you very much. So I mean, let's just write it per row. So per row. Equal to that. Is this question clear or not? Yes or no? There's no mid. There's no like yes or no. So if it's not clear, so it's 100% or no? No. Okay. Is there any part that is unclear? Not related to group actions? No, I can tell you, for example, that could be a question. Show how to construct a surjective homomorphism from S4 to S3. Or I can tell you for example, like the homeworks, for example. These are good steps. But is this clear or not? Is there any problem in here? Where is the main problem? I just want to see where the problem is so that we can fix it. Yeah. S4 mod H, how many elements does it have? S4 mod H has 3 elements, right? S4 mod H, how many left codes that has 3 elements? Exactly. So label them 1, 2, 3. Label them 1, 2, 3. 3 elements in S4 mod H, label them 1, 2, 3. Okay?
Oh.
Okay? Yeah.
How do you know there are 6 opposite squares?
From S4 to, we proved that the kernel of rho has size 6 because it divides 6 and strictly bigger than 3. If you have any problem with this, please ask now. It's better to ask now.
And so for like the last step, we should just have memorized that.
You should have, yeah, you could know. You could know. Is the last step the only problem? You wouldn't have known that. So now you could know. Or you could rederive this. Okay, let's think about something. You need the normal subgroup of size 4. Okay, in S4. You agree that, so the normal subgroup you agree that has size 4. You just have to know what is it. So you need the identity and conjugacy classes. What's the only possible way? I mean, write down your. Exactly. So write down the square. Okay. You remember? So if you look at your square, you know that it's a subgroup of your square of size 4. You agree?
Mhm.
Now, what are the only elements that are? How can you find a subgroup closed by conjugation in your square? It's only these 2 by 2 cycles. Is it clear? Okay. Okay. So you agree that you need a normal subgroup. And your normal subgroup will be in the symmetry of the squares. I mean, you can relabel the square and take the intersection. Sure. It's a normal subgroup of H, but not of S4. Very good question. It's a normal subgroup of H, but not of S4. Why is that? Because you have a 4 cycle. Now, if you have a 4 cycle and normal subgroup, then you have all the 4 cycles in S4. You agree with that or not? So you want a normal subgroup, you want a subgroup of H that is normal in S4 and it has size 4. What is the only possibility? It's a union of conjugacy classes. And you know that the 3 cycles, you have only 2 by 2 cycles, you have only 3 of them. So that's the only possibility. Is it clear or not? If you don't want to memorize this, you can memorize this. Yeah, or you can, I mean, do you want me to explain how to get this normal subgroup from here or not? Yeah, in the last exercise session, we wrote the 3 conjugates of D4, we relabeled the square, and we took the intersection. Exactly. So you can do that. Sure. You can do that. Yeah. Yeah.
If you understand.
Yeah, thank you, sorry. Thank you, Joanna. I've been ignoring the people attending live. What are the Julian? Yeah, Julian, is that clear or not? Yeah.
If you learn and can do every single question from homework 789, you get 4 marks on the.
I mean, I don't know. That's how it happens. If you know and study, then you'll see. Okay. if I tweak it, if I twist the question a little bit, then what happens? If you memorize,
That's what I'm saying, if you understand.
if you understand, then yes, we should be able to do all the questions.
Not if I understand.
Of course. But that's everywhere. If you understand it, then everything will be fair. Out of the 9 assignments, which are the most important? So I mean, I said that the focus should be on 6, 7, 8, 9, and more emphasis on 7, 8, 9. Okay, now there are still things we have to go over. But I think we can call it a day today if you guys want. Or I mean, I can keep going, but we can call it a day. There are things on P groups. There are things on CELO theorems. It's important as well. Yeah. No. You should, the ones you should worry about are CELO 2-3. You just have to know the proofs and the statement of the 3.
They said, don't worry about ISO 2.
Not isomorph, yeah, not the isomorphism here. Okay, so you guys have questions anymore? Any questions you can ask? No more questions. So are these examples well digested? Are we good with here? So at least repeat them. Repeat them. Make sure to know these are the homeworks. Again, if I tell you, use what you know from the lectures or the homework on normal subgroup S4. You can just say, okay, the kernel is a normal subgroup S4, if you have a question like that. And I know this is the only normal subgroup of S4 from my homework. Works. Or if I ask you to rederive it, you should rederive it. You should explain why. Okay? So I can ask you both on questions like that. Okay, the key part is to know everything. Yeah. Yeah. It should be a subgroup first. It should be a group first, and then if and only if it's a union of conjugate sequences. So first you have to show, yeah. So you have to put this as a subgroup, and then it's union of conjugate sequences. Then you win. Okay, is that clear? You have to show it's a subgroup. It's not bad because you have A, B, and A times B, and A and B have order 2, so it's a subgroup immediately. And A and B commutes. AB is equal to BA. A and B commute. And I have order 2. So 1A, B, AB form a subgroup. It's a union of 2 conjugate classes 1 and the 2x2 cycles. Yep, very good. Many ways. Thank you for all the hard work. No problem. Yeah. I mean, I said in class the focus is on 6, 9, right? Like it's not. I'm not giving you any special info. Okay. So if you guys have questions, I can stay to ask, but I will keep so that people can ask. So you can ask from behind the yeah. Why does it divide 3, 5? Okay, guys, let's I mean I have to keep this so that people can ask. Why does it divide 3 factorial? G mod kern rho is isomorphic to rho G, right? Rho G is a subgroup of S3. By Lagrange, the size of rho G will divide the size of S3. Is it clear or not? Yeah. Are we clear? Is it clear?
Yeah.
Clear?
Mod H divides mod G. By like
G mod per row, which is the size of row G, divides S3. Okay, guys, I'm going to ask you not to stand in front. Try to stay away from the camera. Yeah, exactly. Okay, any more questions? Are we good? People attending online, do you have questions?
Thank you.
No problem. Bye-bye. No problem. People attending online, I can take your questions now. Hi, it's the crowd part. What do you mean? You have questions? No, but not on the camera. Oh, yeah. Okay. Okay, yeah. So what is your question? Why the fixed point is in H? I mean, G is acting on H. So a fixed point is a subset of H, is an element of H. What is a fixed point? So it's an H and but the G is equal to G. In your case, it's H and H, such that G star H is equal to H for all G. If GH, G inverse is equal to H for G.
So what is the stabilizer?
Not a stabilizer. Stabilizer or set of fixed points? What are you looking at? What inverse are you, what action are you looking at? It's G acting on H by conjugation or G on G mod H?
G by conjugation.
G acting on a normal subgroup by conjugation. So what is this? An element is fixed if and only if G star H is equal to H for all G and G.
Yes.
Right?
Okay.
So H belongs to H. So the set of fixed point is that H belongs to H such that G star H is equal to H. Agree? For all G and G.
Yes.
So this is H and H such that H belongs to ZG. Agree? Yes. This one will tell you that H belongs to ZG, right?
Yes. Okay.
GH inverse is equal to H will imply that H belongs to ZG.
Yes.
And this one, because H is in H already.
Okay.
That's how we started. So H is and H is ZG. Okay. Guys attending online, people attending online. People attending online. So I prefer to close the online first unless they want to. Could you please fix? Okay. I mean, so private questions, please email them to me. Okay. Don't post them on the chat. Okay. Okay. So please email it to me and I'll fix it. Okay. Yeah.
Stupid.
Yeah, sure. How the intersection of XH, X inverse. Okay. A intersection B, is it contained in A or no?
Mhm.
Okay. X, H, X inverse. This is H. Intersection X1, H, X1 inverse. Intersection X2, H, X2 inverse.
Okay.
Is it contained in H?
Yeah.
Of course, this is not a proof because
Yeah.
this is not necessarily count.
Can we just let?
E.g., exactly. So, I mean, if X belongs to the intersection, or X, so A belongs to the intersection, implies that A belongs to XH, X inverse, for all X and G, right?
Mhm.
If it belongs for all X and G, you can put X equal 1.
Okay.
Implies A belongs to 1, H1 inverse. Okay, which is H. Is that clear now?
That was clear, thank you. Sorry, I just.
No, that's okay. That's okay. It's good.
Thank you so much.
No problem. Have a good day. Have a good day. It's not day anymore. Yeah. Same to you. Thanks.
Big question. So.
Yeah. Okay.
Just see. Stay.
Oh, you won't have to know Cauchy's theorem. You have to know the statement, but not the proof. Yeah. Cauchy's theorem, you just have to know the statement, but not the proof. Use it, apply it, but not the proof.
But it did twice.
Did I do it twice? No, I did it once here at night. And then it was at night, I did it here, I didn't finish it because I had to leave the room.
Oh.
And then I read it the other day. I read it in the Monday lecture. Okay, so you don't have to know the proof, but you just have to know the statement. Okay?
Can you explain?
Why I choose this set?
No. The non-single.
Why the non-singleton orbits have size p? Divides p?
Yeah.
Okay, so G stab, G modulo stab, G divided, yeah, the size of the orbit is the index of the stabilizer.
Yes.
Right? Now your group here has size p.
Yes.
Okay, so the index of the stabilizer, which is the size of the orbit, will divide p. So G stab if G is finite, times tab S will equal G, size of G, right?
Yes,
So this one will divide this one.
yes.
Great. Now, if this one has size P,
Mhm.
then this one is either 1
Or
P. Now, if I tell you if it's not 1, what is it?
why is that?
Because these are the non-singleton orbits by definition. If you look at what I wrote, did I write it's non-singleton orbit?
Okay,
It has size bigger than 1.
so it is divide,
It divides P, and it's strictly bigger than 1.
so it's P.
P, exactly.
So the S here is G to the power of
P minus 1. Why is that? Because this is the cardinality of S.
Yes.
That's
Yes,
clear?
Yeah, so K is also divided by
No.
P.
K is no, not yeah. At the end, that's what you want to get.
Why?
Because G is divisible by P.
Yeah.
And KP is and BP is divisible by P. And QP is divisible by P. This is divisible by P.
Yeah,
And this is divisible by P. QP is divisible by P.
this is P to the power of P minus 1.
It's divisible by P to the power of P minus 1. That's right. So it's divisible by P. Right? 5 divides 30. Right? So
Mhm.
5 divides 30 to the 4.
Okay.
You agree or not?
Yes.
P will divide the cardinality of S, and P will divide QP.
Yes.
So P will divide K.
Okay.
Now you know that K is at least 1, because the identity has singleton orbits. So K is
Yeah.
at least P.
Yes.
So you have more than the identity.
Okay.
Is it clear or not?
Yeah.
100%?
Yeah.
Okay.
So it means that there is only one element in the orbit.
Singleton orbit means there's only one element. It's itself.
So E.g. is
So or S always belongs to orb S, right? Right?
yes.
Because EGS
It's
is S.
Yeah.
So singleton orbits means that S is equal to orb S.
so for this particular question, the singleton orbit, the E.g.
One of them. It's one of them. So EG is a singleton orbit. The orbit of EG is itself.
Mhm.
But it's not only the case. If you have X satisfying X to the P equal EG, then X
is
is
also
also a singleton orbit.
okay.
And that's all of them. That's exactly all the singleton orbits. So if they have X, such that X to the P is 1, then you get a singleton orbit.
So if the orbit is the whole set,
Transitive.
then it's transitive and the orbit is non-singleton.
Unless the set has one element. If the set has one element,
Oh.
yeah, okay.
Okay.
That's the silly example, yeah.
Thank you.
But yeah, that's the silly example. The set has one element and the action is transitive.
Okay.
So, but in general, no. If your set has more than 2 elements and the action is transitive, then you have no singleton orbits. That's right.
So
that's
why
very good.
we need to choose S to be the set of
Oh, why you need to choose that? That's a
Yeah.
good question. I need to choose that just for that the fixed point will satisfy X to the P equal 1. The set of the singleton orbit.
Yeah.
I needed to satisfy that they're all equal, right?
Yeah.
And I need also to satisfy this. Now put these all equal to
what
X,
we're
because there will be invariant under tau. You will shift
always
that.
need to be fixed.
Exactly. This means that, I mean, how do I define tau to act? Tau x1, xp. What is that equal? X tau 1. Exactly. So let's pick tau to be the first one. For example, sigma. I call it sigma. I don't know. Okay. So I need x1 to be equal to x2.
Yeah.
x2 equal to x3
Oh,
if it's fixed.
okay.
Now I also need this to be satisfied. I need an element x of order p. So I need x to the p equal eg. Set them all equal to x. What do you get?
X to the P.
Yeah, exactly.
Okay.
And then you have to do more work. You have to show that tau times this
Mhm.
will also satisfy that by just bringing the x1 there, basically. But that's more clear. Well, that's more difficult, but it's more clear. The clear part. Why do I need this set? Just so that when I look at the fixed points,
Mhm.
I get that xp is the identity. X to the p is the identity.
Yeah.
So first you show that the point is fixed,
Mhm.
if and only if it has this form, x, 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 x.
Yes.
If all the elements are equal. Now it should also satisfy this one. So you should have x times x times x times xp times equal to eg, which means that xp is equal to eg. Okay, is it clear? Great. People in the online questions? You guys have questions? You got a question?
Yeah, why is row of S4 isomorphic to S?
S3. So row of S4, what is the size of row of S4? No, row of S4 is bigger than 3 and divides 6. So it has size 6.
Yeah.
Now what is the size of S3? So row of S4 is isomorphic to a subgroup of S3 of size 6. What is it isomorphic to?
Okay. Oh, itself.
Exact. So it's S3.
What is
Okay.
that according to the
Isomorphism theory. First isomorphism theory. Is that clear?
Yeah.
People online, I'll just shut the chat now. I'll go away. Do you guys have questions?
Yeah.
No problem. Questions? Should you just say bye-bye? Bye-bye? So please ask your questions. No, all good, thank you. No problem, Shivan. People online? I'll wait 1 more minute. I'll wait 1 more minute. If you have questions, please let me know. I'm the only one in the room now, so. Okay. No problem. Okay, hope it was good. I'll start shutting everything down. Bye-bye, everyone. No more questions? Last call? Okay.